All right, let's jump right in. Have you ever really stopped to think about how computers think? I mean, at their core. It's not in English, it's not in pictures, it's all in numbers. Today, we're going to crack the code on the 4 key number systems that form the bridge between our world and the world inside the machine.
Take a look at this. Yeah. To a computer, this wall of ones and zeros is a crystal clear instruction. But for us, it's pretty much gobbledygook. This is binary, and it's the native language for every single digital device on the planet. But man, is it a headache for us humans to try and read.
And that's the big problem we need to solve, right? Computers are totally fluent in binary, but we are definitely not. So how in the world do we figure out a way to communicate with them without drowning in a sea of ones and zeros? That's the key question we're going to answer right now.
I mean, seriously, just imagine trying to find a typo in thousands of digits like the ones we just saw. Just relying on pure binary is not only incredibly slow, it's a recipe for disaster. It's super easy to make mistakes. We had to find a better way.
So we developed a few different languages, kind of like translation layers. First, you have binary, which is base 2. That's the machine's mother tongue. Then you have our good old decimal, base 10, what we use every day. And in between, we have 2 really clever systems, Octal, which is base 8, and Hexadecimal, base 16.
Now you might be thinking, great, 2 more types of math I have to learn, but that's not what this is about. Octal and hexadecimal were actually invented to be clever shortcuts. They're basically a form of shorthand for programmers to handle those long, messy binary numbers.
And here's the secret sauce. The base of the octal system, the number 8, it's not just some random number. It's 2 to the power of 3. And this little mathematical link is the absolute key to the shortcut between binary and octal. Keep that number 3 in your head.
And, you guessed it, the exact same logic works for hexadecimal. Its base, 16, is just 2 to the power of 4. It's this direct relationship to a power of 2 that makes these systems so incredibly useful. And for this one, you'll want to remember the number 4. So because of those awesome power of 2 relationships, we get to use this incredibly simple and visual method to convert between them. This isn't about heavy math at all, it's just about recognizing patterns. We call it the grouping trick, and it's by far the fastest way to translate.
Okay, let's see this thing in action. To go from binary to hexadecimal, you just follow these easy steps. You take your binary string, then, starting from the right, always from the right, you break it up into little chunks of 4. Why 4? Well, because 16 is 2 to the power of 4. Then you just take each of those little 4-bit groups and convert it to a single hex digit. So 1011 becomes B, and 0111 becomes 7. Stick them together and you get B7. That's it.
And the best part, you don't have to memorize what each of these groups equals. You just use a simple lookup table, a cheat sheet like this one. You find the binary pattern and you see what hex digit it matches. The skill isn't about memorization, it's just knowing how to use the tool.
And what's so elegant about this is that it works perfectly in reverse too. To go from hex back to binary, you just expand each digit into its 4-bit group. And if you were using octal, you'd use groups of 3, right? Because 8 is 2 to the power of 3. It's the exact same beautiful logic.
Okay, so now we can switch back and forth between the machine's language and its shorthand versions. But what about us? How do we get back to our native language, decimal? For that, we need a couple of other tricks up our sleeve.
The first method is for converting any of those other bases, whether it's binary, octal, or hex, into our normal decimal system. It's called the weighted sum method. And it sounds kind of fancy, but the idea is actually super simple. Every digit's position in a number has a specific value or a weight.
Let's just walk through one. Let's take the hex number 1A3. We're going to work from right to left, starting with position 0. So the 3 on the far right is in the zeros spot. We multiply it by its base, 16, to the power of 0. Anything to the power of 0 is just 1, so that gives us 3. Next up is A, which, remember, is just 10 in hex. It's in the ones position, so that's 10 times 16 to the power of 1. And finally, the 1 is in the 2's position, so that's 1 times 16 squared. You just add those results up, and boom, you get 419.
But what about going the other way, from our decimal system into another base? For that, we use a simple process called repeated division. So let's say we want to turn the number 13 into binary. We just keep dividing by our target base, which is 2. So 13 divided by 2 is 6, with the remainder of 1.
Okay, now we take the 6. 6 divided by 2 is 3, with a remainder of 0. Now we take the 3. 3 divided by 2 is 1, with a remainder of 1. Last one, 1 divided by 2 is 0, remainder 1. Once you hit a quotient of 0, you stop. And here's the crucial part. You read those remainders from the bottom to the top. So that gives us 1, 1, 0, 1. The number 13 is 1101 in binary. So, the point is, we now have a full-blown toolkit for translation. But you might be thinking, okay, that's a cool party trick, but why does this actually matter? Where am I going to see this in the real world?
Oh, you'll see it everywhere once you know what to look for. When programmers are digging through code trying to find a bug, all those memory addresses and error codes are almost always in hex. It's just so much cleaner than binary. If you've ever picked a color for a website, you've used hex color codes. That's exactly what hashtag FFFFF for white is. And for the engineers who are designing the actual computer chips, this is the fundamental language they use to build our digital world.
So, there you have it. What started out as a complete jumble of ones and zeros is now a structured set of languages that you know how to translate. You've basically been given the secret decoder ring for how information is stored at its most fundamental level. You can now read the language of machines. So the only question left is, what are you going to do with it?